we have talked about how we can classify soil using the Unified Soil Classification System. Now, we want to talk about the important soil parameters that are commonly used in foundation design. So first of all, in foundation design, we care a lot about how we can capture the shear strength of soil. Basically, shear strength of soil means the shear stress at which shear failure occurs. And shear stress is a type of stress that is basically parallel to the cross-section of the material. So in this section, we're going to talk about the shear strength parameter that we are going to use in the foundation design. However, before that, we want to introduce an important concept in geotechnical engineering, which is the concept of effective stress. So if we have to evaluate something called the total stress of soil at a particular depth, basically the way to determine it would be to calculate the amount of soil and water and any type of material that is above that particular soil location. However, this total stress will have two sources. The sources of total stress would be the stress that is carried by water and the stress that is carried by the soil solids. For effective stress, we only care about the stress that is carried by the soil skeleton. So in order for us to evaluate the effective stress of soil at a particular depth, we will need to first evaluate the total stress at that point and then subtract the water pressure at that point. And then we will obtain the effective stress, which is equal to the stress that is carried by the soil skeleton. So as mentioned previously, we want to have some parameters that can help us evaluate the shear strength of soil. For marine sediments, since it is saturated, so we will use the Mohr-Coulomb failure criterion in total stress and effective stress to help us evaluate the shear strength of soil. So for the Mohr-Coulomb failure criterion in terms of total stress, we will need to use the total normal stress. And then for the parameters, we will need to use the cohesion and then also the friction angle determined based on total stress states. If we use effective stress, that means we will need to use the effective normal stress and then also the cohesion and friction angle that is determined based on effective stress. So let's look at how we can evaluate these shear strength parameters based on some laboratory tests. The commonly used laboratory tests would be the direct shear test and triaxial test. For direct shear test, basically it would contain a shear box, and the shear box is split into two halves. We would apply a normal stress on the top of the shear box, and then to perform the test, we will basically move one half of the box relative to the other one, and then we will track the shear displacement and then also the shear stress of the soil inside the shear box. So the typical results for a direct shear test would be a plot of shear stress versus effective normal stress. For the direct shear test, since we cannot control the drainage of the soil specimen, the test is basically considered as a drain test. For clay material, as mentioned previously, the hydraulic conductivity is very small. So when we perform a direct shear test on clay material, we will have to perform the test very slowly, such that we will not have any excess water pressure generation. So from a direct shear test, we will obtain a relationship of shear stress and effective normal stress. The slope and the intercept of that relationship would be the C prime, which is the effective cohesion, and then also the slope of the line would be basically the friction angle, which is the phi prime. Another type of test that can help us to determine the shear strength parameters would be the triaxial test. For triaxial test, there are different ways to perform it, depending on whether we allow drainage during the test. First of all, for a triaxial test, we will have a triaxial chamber. We will put the soil specimen inside the triaxial chamber and then fill the chamber with water. There are two stages in a triaxial test. The first stage will be a consolidation stage, and then another stage will be the shearing stage. For the first stage, during the consolidation stage, basically we will apply an all-around stress to the specimen, and then for the second stage, which is the shearing stage, we will apply an additional axial load in the vertical direction. So for triaxial test, basically we can perform the test in 4 different ways. And then they are the consolidation drain test, consolidated undrained test, unconsolidated undrained UU test, unconfined compression test, which is the UC test. So depending on whether you want to obtain parameters that is under drained or undrained condition, we will choose one of these 4 to obtain the soil parameters. So for example, if you want to obtain the parameters that is under drain condition, then we will perform the CD test, the consolidated drain test. So during the consolidated drain test, during the consolidation stage, when we apply the all-around stress, the soil will be under drain condition. That means the soil would likely to undergo some deformation and settlement. During the second stage, we will perform the test by allowing drainage. That means when we shear the specimen by adding the additional load in the vertical direction, the soil would be going through settlement as well. And from the CD test, we can obtain shear strength parameter C prime and phi prime. Basically, this relationship can be obtained by plotting the shear stress versus normal stress. If we want to determine the undrained behavior of soil, and if we have pore pressure measurements, we can perform CU test. So unlike what we did in the CD test, during a consolidated undrained test, during the shearing stage, we will not allow drainage. End result of not allowing drainage will be that during the shearing stage, the excess pore pressure will be positive or negative depending on the state of soil. But the bottom line is that during the shearing stage, no deformation would occur and excess water pressure would be generated. So again, by plotting the shear stress versus normal stress, we can obtain the shear strength parameter C and phi. If we want to obtain the undrained effective stress parameter, we will measure the pore water pressure, and then with the effective stress Mohr circle, we can determine the C prime and phi prime under undrained condition. And then for the total stress Mohr circle, we can also generate the same Mohr-Coulomb failure envelope, and the shear strength parameter will be in terms of total stress parameter. But for both effective and total stress failure envelope, they are corresponding to an undrained condition. The third type of triaxial test would be the UU test. Basically, for the UU test, during the addition of confining stress, which is the first stage, we will not allow drainage. So there will be no deformation during the first stage. So it doesn't matter what kind of confining stress you apply to the soil, because basically all of them would yield the same answers for the second stage. Second stage is the shearing. So during shearing, like what we did in CD and CU test, we will apply additional vertical stress in the vertical direction, and then we will plot again the Mohr circle. The Mohr circle will be in terms of total stress, because for a UU test, we will not track the excess water pressure generation. So all we can do will be to plot a total stress Mohr circle. And then basically, the radius of the Mohr circle will be corresponding to the undrained shear strength, which is also the total stress cohesion. For this particular test, we will have a phi diffraction angle equal to 0. The last triaxial test that we can perform will be the UC test, unconfined compression test. Basically what it means is we don't have the first consolidation stage. So we will directly apply vertical loading to the vertical direction of the specimen, and that the confining stress is basically equal to 0. So from this, we can still plot the total stress Mohr circle, and then the radius of the Mohr circle is again the undrained shear strength, and the diameter of the Mohr circle would be the so-called unconfined compression strength. In this section, we have learned that for foundation design, we need to obtain some design parameters. Typical design parameters would be the cohesion term and then also the friction term. But these friction and cohesion terms can be obtained from different laboratory tests. Depending on the loading condition, for example, undrained or drained condition, you can choose to perform different lab tests to obtain the appropriate shear strength parameters for the foundation design.